Hello viewers, my name is Dr. Ajay, Associate Professor, Department of ECE, Institute of Aeronautical Engineering College, Hyderabad. Today we are going to discuss the topic on definitions, terminology on arrays and measurements. So this topic is related to the codes, antennas, waves and propagation. So let us start our session. Let us see some basic definitions. On antenna arrays. Or what is an array? So why we are going for arrays? So to increase the directivity and the field strength in the desired direction, a group of antennas are required to excite simultaneously. Such a group of antennas is called array of antennas or simply antenna array. Suppose if there is a single antenna, this is known as one element. If we place n number of antennas adjacent to each, so a group of elements form an array. So here, what is the main advantage of an array? So why we are going for arrays? So here, whenever there is an antenna, this antenna will radiate electromagnetic energy to some distance only, to some finite distance only. So if we want to increase the distance of propagation, then we need to increase the length of the antenna or the height of the antenna. But this is not practically possible. So practically, it is impossible for us to design an antenna with a longer length for increasing the distance of propagation. Hence, we are going for an array. That is, to increase the directivity or to increase the distance of propagation. So we are going to place adjacent elements adjacent to each other, adjacent antennas, each other with equal spacing in order to increase the directivity in the desired direction. So thus, an antenna array can be defined as the system of similar antennas directed to get required high directivity in the desired direction. Antenna array is a radiating system in which several antennas are spaced properly so as to get greater field strength at a far distance from the radiating system by combining radiations at points from all antennas in the system. So here, this is known as an antenna or a single element. Let us assume this as 1. There is another element is placed here. Let us assume this as 2. Another antenna is placed adjacent to each. This is 3. So here every element of an array radiates some minimum amount of electromagnetic energy. Let us assume this the amount of radiation is E1. The amount of radiation produced by 2 is E2. The amount of radiation produced by 3 is E3. So here the total radiation produced by all the elements of an array is equal to the radiation produced by each of the individual element of an array. So here the total electric field strength is given by as E is equal to E1 plus E2 plus E3. That means here all the radiations produced by all the antennas in the system, we need to do the summation, vector summation of all the radiations produced from all the antennas in the system. We are going to calculate the total electric field strength produced by the antenna array system. In general, the total field produced by the antenna array at a far distance, it is the vector sum of fields produced by the individual antennas of the array. The individual element is generally called the element of an antenna array. An antenna array is said to be linear if the elements of the antennas are equally spaced along a straight line. So here, when an antenna array is said to be a linear, an array is said to be linear when all the elements of the antenna are spaced equally along a straight line. Then we call it as an linear array. A linear antenna is said to be uniform linear array if all the elements are fed with equal current of equal amplitude with progressive uniform phase shift along the line. That means here if there are 4 elements, 1, 2, 3, 4 and 5. There must be a uniform progressive phase shift between the elements. Then the type of antenna array we call it as uniform linear array. Here there is a uniform phase shift of 5 degrees between the 2 elements. And here there is a between 2 and 3 there is 10 degrees, that is the phase shift. And between 3 and 4 there is a phase shift of 15 degrees. And between 4 and 5 there is a phase shift of 20 degrees. So here we are going to design the elements between the we are going to design a uniform linear array with a phase shift of uniform progressive phase shift. That means here there is a difference of 5, here the difference is 5, and here the difference is 5. But there is a progressive phase shift of 5 degrees, 5, 10, 15, and 20. So the linear antenna array is said to be uniform linear array if all the elements are fed with a current of equal magnitude with progressive uniform phase shift along the line. The element in the antenna array is lambda by 2 dipole. The length of half wavelength dipole may not be equal to the electrical wavelength. If the variation of the electrical length from lambda by 2 is 5%, then it is assumed that the radiation properties of individual elements are not affected. So generally, all the elements of an array, the length is taken as lambda by 2. The length of all the elements of an array is taken as lambda by 2. The length of half wave wavelength may not be equal to the electrical wavelength. The length of half wave dipole may not be equal to the electrical wavelength. So there are different types of arrays we are having. One is broadside array, end-fire array, collinear array, and parasitic array. So what is a broadside array? So the broadside array is one in which a number of identical parallel antennas are set up along a line drawn perpendicular to the respective axis. So in the broadside array, the individual antennas are equally spaced along a line, and each element is fed with equal current of equal magnitude, all in the same phase. So here, all the elements in a broadside array are arranged on a straight line, and the direction of maximum radiation will be perpendicular to the direction of the axis, to the direction of axis of the array. So if we assume this as array axis, the radiation will be perpendicular to this axis. So this is, we call it as a broadside array. That means this setup of arrangement where there is a maximum amount of radiation perpendicular to the axis, then we call it as a broadside array. The end-fire array. Here it is nothing but a broadside array except that the individual elements are fed in out of phase, usually 180 degrees. So in an end-fire array, a number of identical elements are equally spaced along a line, and individual elements are fed with currents of equal magnitude, but their phases varies progressively along the line in such a way as to make the entire arrangement substantially unidirectional. So here in an end-fire array, all the elements are arranged in such a way that of equal magnitude, their phases varies progressively so that the radiation pattern will be unidirectional. That is, in one particular direction only, the radiation is possible in an end-fire array. Collinear array. The collinear array consists of two or more half-wave dipoles which are placed end to end. So these antennas are placed on a common line or axis, being parallel to each other. So collinear is nothing but one over the other. So we are going to place the antennas one over the other. These are stacked one over the other like this on one common line. So here this is a common line. This is an axis. These are all the elements are arranged in collinear fashion. So the maximum radiation in these arrays is broadside, that is perpendicular like this to the line of array. So these arrays are also known as the broadcast or unidirectional arrays. The frequency range in which the collinear array antennas operate is 30 MHz to 3 GHz, which belong to the VHF range. The fourth one is a parasitic array. So in the parasitic array, the best example of a parasitic array is it is an Yagi-Uda antenna or Yagi-Uda array. So in order to overcome feeding problems of the antenna, sometimes the elements of the array are fed through the radiation from the nearby element. So the array of antennas in which the parasitic elements get the power through the electromagnetic coupling with the driven element which is in proximity with the parasitic element is known as a parasitic array. So here only one element is given the input signal, and all the elements get energy through the process of electromagnetic coupling. Hence the name is given as parasitic array. So parasitic means the elements which are going to get the energy in an indirectly way. That means RF power is fed to the element indirectly but not directly. So the simplest form of parasitic array consists of one driven element and one parasitic element. Here in multi-element parasitic array, there may be one or more driven elements. So common example of parasitic array is a linear half-wave dipoles as element, that is Yagi-Uda antenna. So the array of 2 point sources. The array of point sources is nothing but the array of anisotropic radiators occupying zero volume. So for greater number of point sources in an array, the analysis of antenna array becomes complicated and time consuming. So the array of point sources is nothing but the array of isotopic radiators occupying the zero volume. So for greater number of point sources in an array, the analysis of antenna array becomes complicated and time consuming. So we can derive the expressions of electric field strength for three different cases. One is array of point sources with equal magnitude and same phase. The second case is with equal magnitude and opposite phase, and and the third case is unequal magnitude and unequal phase. So these are the three different cases. Already we have seen the electric field strength derivation of array of 2 point sources. So these are the three different cases: 2 point sources with currents of equal magnitude with same phase, 2 point sources with currents of equal magnitude but with opposite phase, 2 point sources with currents of unequal magnitude and with opposite phase. So here the 2 point sources with the currents of equal magnitude are separated by origin here. So for this we already have an expression here for the E. We need to find out the electric field strength. The E is given by, so when E is given by 2 E naught cos psi by 2. So for this equation, E is equal to 2 E naught cos psi by 2. This is the equation for the arrays of 2 point sources of equal magnitude and same phase here. So the multiplication pattern here, it is a method used to derive, to draw the radiation pattern of any number of elements through inspection. So if we want to draw the radiation pattern of n number of elements, we need to know the radiation pattern of the elements of 2 or 4 or 8. So the spacing must be separated by either by the lambda by 2. We need to know the radiation pattern, and we need to draw the radiation pattern for lambda. 2 elements separated by lambda and 2 elements separated by 2 lambda. So if we know the radiation patterns of these three, then it is easy for us to draw the radiation pattern of n number of elements. So first we need to understand the radiation patterns of lambda by 2 spacing, or with lambda spacing, and 2 lambda spacing. So 2 elements are separated by lambda by 2, 2 elements are separated by lambda, and 2 elements are separated by 2 lambda. So we need to draw the radiation pattern. So from these radiation patterns, we can easily analyze the radiation pattern of 8 number of elements, 16 elements, or 32 elements. So what is multiplication pattern? The total field pattern of 9 isotopic per single sources. It is a multiplication of individual source patterns and the pattern of an array of isotopic point sources, each located at the phase center of individual source and having the relative amplitude and phase. So whereas the total phase pattern, it is the addition of phase pattern of the individual sources and that of the array of isotopic point sources. So whenever we want to draw the radiation pattern through the method of pattern multiplication, first we need to know the radiation pattern of each individual element. So that radiation pattern has to be multiplied with the pattern of all the elements of the array. So which we call it as a group pattern. So a group pattern is nothing but the pattern obtained from all the elements of an array, and the pattern obtained by each individual element we call it as an unit pattern. So unit pattern multiplied with the group pattern will get the resultant pattern. We'll get the resultant pattern, which we call it as the principle of pattern multiplication. So a linear array. So a linear array is nothing but 2 elements are separated by equal current and equal phase. We call it as a linear array. So already we have derived the expression of linear array. So the total far field of the linear array is given by the electric field produced by each of the individual element of an array. So let us assume the electric field produced by each of the individual element is E naught, and first element E naught e power E naught j psi, the second element E naught e power 1 j psi, and E naught e power 2 j psi. So I think we need to derive the expression. The next one is binomial array. So the discussion of n-isotopic sources of equal amplitude but arrays of non-amplitude are also possible. So binomial array is preferable where minor lobes can be completely eliminated. So in most of the cases, a linear array or a broadside array or any type of array, so we observe many number of minor lobes from the major lobe. So our intention is to eliminate all the minor lobes, or we should try to reduce the minor lobes from the radiation pattern drawn from an array. So uh, reduce the reduce the minor lobes, we are going for the binomial array. So it is found that with uniform linear array, as the array length is increased due to the directivity, the secondary or the minor lobes will appear. But for certain applications, it is highly desirable that secondary lobes should be totally reduced or minimized to the desired level. So here, whenever we want to reduce the minor lobes, we need to satisfy two conditions. One is the spacing between the two consecutive radiating sources does not exceed lambda by 2. So whatever the elements we are going to take, either it may be 2 elements or 4 elements, the spacing must not be greater than lambda by 2. The spacing between the elements must not be greater than lambda by 2. And the second condition is the current amplitudes in radiating sources are proportional to the coefficients of successive terms of the binomial series. So whatever the elements we are going to take, those the current input current given to those elements must be proportional to the coefficients of the successive terms of the binomial series. So here we are going for next antenna measurements. So the another concept here is the definition is antenna measurements. So whenever we are going to measure, suppose we have designed an antenna, so we need to measure the performance of the antenna. So to need to measure the performance of the antenna, we need many devices. There may be some errors occurring in measuring the basic parameters of the antenna. So the basic parameters of the antenna are gain, directivity, half power beam width, polarization, efficiency, beam width. So all these are known as the parameters of the antenna. So whenever we are trying to measure these parameters from the antenna that we designed, there is a possibility that some measurement errors will be occurring. Right? So we need to know. We need to study what are the measurement techniques available for us to decide the performance of the antenna. So the antenna measurements are needed to know the actual performance of the designed antennas and also where they have to be used. So there are no accurate antenna measurements practically. So these theoretical concepts can be used to estimate the predict the actual performance of the antennas in terms of the gain, pattern, polarization, bandwidth, and efficiency. So the most common antenna measurement is used. Most of the properties of antenna are directional pattern, gain, or phase pattern in the far field. So we measure the radiation pattern only in the far field. That is, the condition is R is greater than 2d square by lambda. So here the measurement of radiation is shown in the figure. The basic procedure to find out to draw the radiation pattern is here. There are two types of antennas. One is the antenna under test, that is, which is located at the center of the three-dimensional plane, and there is a source antenna here. There is a source antenna here. So the basic procedure is to place the transmitting and receiving source antenna at different locations with respect to the antenna under test, and thus get a number of samples of the pattern at different locations. So here, let us assume here this antenna under test, it is the transmitting antenna, and this is the receiving antenna. So the source antenna has to be moved around the AUT at different locations, and we need to find out what is the electric field strength at this point E1, at this point E2, and at this point E3. So all these arrangement will have good accuracy if the medium selected is in any choice chamber. So we need to perform the experiment to decide the performance of the antenna in a closed chamber, which we call it as any choice chamber. So the antenna under test there is a reciprocity theorem. That is the antennas which acts as a transmitting antenna, receiving antenna. So they follow the reciprocity theorem. So whether they act as a receiving or transmitting antenna, this is due to the applicability of the reciprocity theorem. However, to apply the reciprocity theorem in practical antenna measurements, so the conditions measured to be satisfied are the medium must be linear, passive, and isotropic. So if D is proportional to epsilon E, then the media is said to be linear. So the media must be passive, so we must get the energy from the main antenna through the process of electromagnetic coupling, and isotropic. That means point source which radiates uniformly in all directions, we call it as an isotropic. So the media must be either linear, passive, and isotropic. The EMFs in the terminals of the interchange antennas are of the same frequency. The power flow must be same in the either direction. So in standard careful measurement, the first condition can be satisfied always, and the second can be met without problems. So the third condition is perhaps the most difficult and may lead to the statement that there is no accurate antenna measurement. A near field and far field. So it has been identified that one can find several regions of the radiated field in the vicinity of the antenna. So surrounding the antenna, there are different zones are there. One is the near field zone, the other one is the far field zone. So when R is greater than 2 d square by lambda, we call this zone as far field zone. We call this region as a far field zone. So there are reactive near field zone, radiative near field zone, or Fresnel zone, and the far field or Fraunhofer zone. So this third zone is also known as Fraunhofer zone, and the immediately surrounding the region immediately surrounding the antenna, we call it as the near field zone. The near field zone. So where 0.68 is less than root of 2 d square by lambda. So in the near field zone, the radiation pattern is not clear here. In the radiating near field zone, there is a formation of radiation pattern, and E and H are formed but not perpendicular. And in the far field zone, E and H are formed, the radiation pattern is clear, and E is perpendicular to H. E is perpendicular to H. So the coordinate system, the important parameters of the antenna measurement are radiation properties. Since the radiation patterns of the antennas are having three-dimensional variations in the space, so we can consider spherical coordinate system. So whenever we design an antenna, so we want to measure the parameters, we need to study the basic spherical coordinate system. Why? Because we are going to measure the antenna performance in 3 dimensions. The radiation pattern will be 3-dimensional. So in triply standard spherical coordinate system, the elevation angle measured from the axis and psi is the azimuthal angle measured from the x-axis, and r is the radius of the sphere. So the elevation angle, it is from this, we are going to measure here the elevation angle from yz axis, and the azimuth angle in the plane of xy plane here, we are going to measure in the xy plane the azimuth plane, and r is the radius of the sphere. R is the radius of the sphere. There is another angle known as polar angle theta. So when we move a point from y to z in anti-clockwise direction with a distance of r, it makes some angle theta. So this angle we call it as a polar angle theta. So suppose there is a point in the 3-dimensional representation in the yz plane. When we move this point whose length is r in anti-clockwise direction, this line makes an angle theta in the direction of yz. So the angle so formed, we call it as a polar angle. So there are sources of error. Though we have designed an antenna perfectly, we get some sources of errors while measuring the parameter like gain, directivity, or half power beamwidth. So these sources of errors are there are different types of sources of errors occurring. So errors due to the misalignment of the antenna, errors due to the coupling in the reactive field, so errors due to the man-made interface, errors due to the atmospheric effects, so errors due to the cables, and errors due to the impedance mismatch, errors due to the imperfections of the instrument. So these are the different sources of error generally occurring while we are going to measure any parameter like gain, directivity, or half power beamwidth. So the antenna pattern, these are the 3 antenna parameters. There is a setup required for measurement of gain, for measurement of directivity, and for measurement of radiation pattern. So for the radiation pattern measurement, the antenna under test, that is the primary antenna, is kept stationary. So while the secondary antenna is moved around the primary antenna along a circular path with uniform radius. If the secondary antenna is a directional one, it is always aimed at the primary antenna. So in this process, usually the primary antenna is transmitting. So at different points along the circular path, the readings of the field strength and the direction with respect to the primary antennas are recorded. So then from these readings, a plot of the radiation pattern of an antenna is plotted either as a rectangular plot or polar plot. So whenever we indicate an antenna, so we need to take another antenna. So we need to move the antenna in different directions around the antenna. If this is the transmitting antenna and receiving antenna, we need to find out the electric field strength at different points, and we need to join all those points. The plot obtained is known as the radiation pattern. The plot obtained is known as the radiation pattern of from the receiving antenna. So in the second process of radiation pattern measurement, both antennas are kept stationary with a suitable spacing between them. The secondary antenna is placed aimed at the primary antenna. The primary antenna is rotated about a vertical axis. So in this procedure, the secondary antenna is used in the transmitting mode so that the field strength reading and the direction of primary antenna with respect to the secondary antenna is made. The continuous readings at different points during the rotation can be made using pattern recorder. So generally at low frequencies, first processor is used, while at high frequencies, second one is preferred. So this is the basic setup required for radiation pattern of an antenna. So there is an antenna rotator, receiver, and transmitting antenna. The primary antenna is a transmitting antenna, and this is the receiving antenna. So we need to rotate this antenna. This is stationary. And this antenna must be rotated through a rotator mechanism. And at different points, we need to find out the electric field strength received by the antenna under test. So for gain measurement, we are having two methods. One is a 2 antenna method, a 3 antenna method, and also direct comparison method. So this is the basic setup required for measuring the. So this is the basic setup required for measuring the absolute gain of the antenna by 2 antenna method. And these are the equations we have derived from the fixed transmission formula. Already we have discussed in our theory classes here. So how to get the what is the amount of gain through the fixed transmission formula. So we want to find out the value of gain. So we should know the power received, amount of power transmitted, and what is the distance between the two antennas, and what is the frequency applied for the transmitting antenna. In the 3 antenna method, we are going to use 3 antennas. So we need to combine G1 and G2 as transmitter receiver, and we need to combine G1 and G3, and we need to combine G2 and G3. So by combining these 2 antennas, so we need to apply the fixed transmission formula as above. And we are getting 3 different equations, G1 plus G2, G2 plus G3, and G1 plus G3. By simplifying these equations, we will get the value of G1, G2, and G3. So there are 3 independent variables and 3 equations. Hence it is very easy for us to find out the values of G1, G2, and G3. So in direct comparison method, we are going to use the standard gain antenna. So in this method, the gain measurement is done by comparing the strengths of the signals transmitted by the antenna under test and the standard gain antenna. So the antenna whose gain is accurately known and can be used for the gain measurement of other antennas is known as the standard gain antenna. So there are 2 antennas. With these 2 antennas, we are going to perform the antenna, and we are going to take another antenna which is known as standard gain antenna. The standard gain antenna is the antenna whose gain is already known. So here there is a formula to find out the gain of the practical antenna given by GAUT is equal to G reference into power received by the AUT by power received by the reference. So this is a formula to find out the gain by direct comparison method, whose reference antenna gain is already known. This is the standard gain antenna. So the directivity is given by from the radiation pattern of antenna. So directivity can be obtained from the radiation pattern of the antenna. The directivity of the antenna is defined as the ratio of maximum power density to the average power radiated. So we are having some equations here. So GD is known as PT max by PI by 4 pi R square. So here for references of this all these topics, we can refer John D. Cross, the antennas of propagation by Bakshi, Kerry Prasad by antennas of propagation. So for all the definitions and terminology of RS and measurements, we can go for John D. Cross, Bakshi, and Kerry Prasad. So let us close the session. Thank you.
Like, share, and subscribe. Hit the bell icon for more updates.